This screencast is on kinetics. It's specifically on integrated rate laws and determining the order by looking at a graph. Okay, so all along we have determined the rate order by looking at the experimental data and doing mathematics calculations. Sometimes you will have data presented to you that you can then graph. And based on where you get a straight line graph, you will be able to decide what order it is. So when you graph, if you get a straight line, whether it is proportional or disproportional, as long as it's straight, that will tell you what the order of the data is giving you. So the first graph that you need to do, you're going to do these in order, sequential order. So the first one would be, you would graph concentration versus time. If you get a straight line when you graph concentration versus time, it is considered to be a zero order graph. If it's not a straight line, then you proceed on to the second graph, and you would graph natural log of concentration versus time. If that graph produces a straight line, you can label it as a first order reaction. If it's still a curved set of data, then you proceed on to the third graph, and then you are going to calculate 1 over concentration. So that should look like this if you had the math function here. It looks a little weird on my screencast, but if you graph 1 over concentration versus time, you should get a straight line by now, and that would be second order. So if you are not careful when you're graphing and you don't have scale and you're not able to interpret your results correctly, you may have missed your first order and assumed that it was a curve. I'm sorry, you may have missed your straight line and assumed that it was a curve, so be careful. When you get a straight line, that graph has a slope. That straight line has a slope, and that is how you find the K for that specific order of rate law. So this applies to the first order. When you have first order, you are graphing, to begin with, you're going to graph concentration versus time. And as you can see in this graph, the data presents a curve. If it is not a straight line, then you move on to the second graph, which is the natural log of concentration. So here we go, natural log. And as we look at the data generated in natural log versus time, you can see that you have a straight line. It's visually linear. That will tell you then that your reaction is first order. And what that means is that the exponent is a 1. And you are then able to take some information and look at what's called the integrated rate law. What they have done is they have looked at 2 different times in that slope, and they have generated an equation. And it kind of follows the y equals mx plus b equation, which makes sense since we said that the straight line generated from that data is our slope, which is k. So our k value is the same as the slope. Now, you will need to know this equation. It will allow you to calculate K, or time, or concentration, depending on whatever circumstances you have. A to the 0 is the original concentration at time 0, and A to the T is the concentration at that specific time. So for instance, if they say at 20,000 seconds, you're going to plug 20,000 into the T here, the time, and you're going to then use the corresponding concentration in your calculation. This will allow you to determine the initial concentration, or if you know the initial and the concentration at time 20,000, you could find the K value. There's also another linked equation that goes with these integrated rate laws, and they are for half-life. Half-life is how long does it take for half of your sample to disappear. In a first order reaction, half-life is equal to the natural log of 2 over k. Please add that 2 in there. So it is not a variable value, it is a constant. And if you take the natural log of 2, it is 0.693. So you could say that the half-life is 0.693 over k. And that will get you the constant or the half-life. All right, so if you had graphed the concentration versus time and got a curve, and then you graphed the natural log versus time and got a curve, you would then proceed on to the third graph, which is, here we'll label this one in a second. The third graph is the 1 over the concentration of NO2 in this case versus time. And in this case, you see that you get a straight line, you get a linear graph, and that tells you that it is a second order reaction. And again, because it's a second order reaction, we have the ability to know some more information about the slope, or I'm sorry, the constant. So the integrated rate equation that you'll need to know for this is 1 over the concentration, and this would be at time t also, equals 1 over a to the 0 plus kt. The k is still equal to the slope of the straight line graph. For the half-life, you have 1 over the initial concentration times the k value. Here is a handy chart that helps you wrap your head around all the things that were given in this screencast. The rate laws, the integrated rate laws, and the half-lives, as well as the linear plot. You can see for the 0 order, the first order, and the second order. You will, I'm going to have to double check, you will need to know which plot is which straight line. But as far as the rate law and the half-life equations, you'll have to ask me about them later.